We will be learning about two different types of solutions in this lecture. They are the ideal solutions and the non-ideal solutions. Now, to begin with, let's see what is the basis on which we classify them. So, this is based on the Rawls law. Based on the Rawls law, there are two types of solutions. One, ideal, and two is non-ideal. So based on the Rawls law, there are two different types of solutions, ideal solutions and non-ideal solutions. We'll start with the first one, that is the ideal solutions. So let's see how do we define or how do we categorize a solution as an ideal solution. So what is an ideal solution? A solution that obeys Rawls law. A solution that obeys Rawls law over the entire range of concentration. A solution that obeys Rawls law over the entire range of concentration. Such a solution is known as an ideal solution. So ideal solution obeys Rawls law. It will obey the Rawls law. Now let's say we have a solution in which A denotes the solvent and B denotes the solute. So if A is the solvent, B is the solute, and the solution is ideal, that means it will obey the Rawls law. Then as per that, if you remember, PA should be equal to P naught A into chi A, and PB should be equal to P naught B into chi B. If you remember the statement of the Rawls law, the partial pressures of the components are directly proportional to their mole fractions chi A and chi B. So if the solution is ideal, PA will be equal to P naught A into chi A, PB will be equal to P naught B into chi B, and P total will be equal to PA plus PB. Now, these ideal solutions, when they are formed, it is observed that delta H mixing. Now, what is delta H mixing? It is the enthalpy. Okay, it is the enthalpy change during mixing, when you mix the components and you make the solution. Okay, so in case of an ideal solution, delta H, that is the enthalpy change during mixing, is 0. It is equal to 0. So delta H mixing is equals to 0. What is the meaning of this? Enthalpy is 0. That means no heat is evolved or absorbed. No heat is evolved or absorbed during the process, during the formation of an ideal solution. At the same time, it is observed that delta V mixing. Okay, what is delta V mixing? It is the volume change, the change in volume. When you mix the two components, that is the solute and the solvent, then delta V mixing, that is the change in volume, is also 0. So delta V mixing is also equals to 0. And what do you understand by this? That there is no change in volume. There will be no change in volume. That is, the total volume before mixing remains same as the total volume after mixing the solute and the solvent. There will be neither an increase nor a decrease in the volume. So delta V mixing is also equals to 0. Now we have to understand what is the reason behind this, that some solutions, they behave ideal and there is no change in enthalpy or there is no change in volume. So for that, let's say AA represents the solvent interactions. Okay, solvent interactions. See, if you take any solvent, let's say water, then within the solvent, the molecules of the solvent are also going to interact with each other. So that interactions we are representing as interactions, or the solvent interactions. Likewise, let's say BB represents the solute to the solute interactions. Okay, so the solvent will have solvent-solvent interactions, the solute will have solute-solute interactions, and when you mix the solvent and the solute to form the solution, a third type of interactions will result in, and that is AB. So what will be AB? AB is going to be the solvent-solute interactions. So in a solution, okay, when you mix AB and you make a solution, in a solution, all these three interactions will be there. Okay, A will be interacting with A, B will be interacting with B, and A will be interacting with B also. So these are the three types of interactions that will be there in the solution. Now in an ideal solution, it is observed that the magnitude of AA and the BB interactions, magnitude of AA and BB interactions is nearly same as that of the AB interactions. Okay, so what is it? You can say these are the interactions which will be there before mixing, before you mix the solvent on the solute, and these are the interactions that will be resulting in after mixing the solute and the solvent. So it is observed that in an ideal solution, the solvent and the solute interactions are nearly of the same magnitude, okay, as that of the solvent solute interactions. So the three types of interactions are nearly the same, and this is the main reason behind that these solutions behave ideally, because there is not much change. The type of interactions which were there earlier remains almost the same as the interactions which are formed later on mixing the solute and the solvent. So there is not much change, you can say, and that's why this solution behaves as an ideal solution. 100% ideal solution is not possible, but there are solutions which are, near to ideal. They behave very near to ideal. So I'm giving you now some examples of such solutions. So these are the examples of nearly ideal solutions which are very much near to the ideal behavior. So examples of nearly ideal solutions. Number one is when normal hexane is mixed with normal heptane. Okay, when normal hexane is mixed with normal heptane, the solution behaves ideal. You know why? Because hexane and heptane, they are alkanes, and the interactions which are possible in alkanes are the van der Waals interactions or the van der Waals forces. Now what happens is, within hexane there are van der Waals interactions. Within heptane also there are van der Waals interactions, and when you mix hexane and heptane, even then the nature of the interactions is going to remain van der Waals. So when the initial and the final interactions are almost the same, the solution behaves ideally. Second example is taken is of CH3Cl mixed with CH3Br. See, this is chloromethane and this is bromomethane. In alkyl halides, we've already studied in organic chemistry that the halogen, being more electronegative, withdraws electrons towards itself, taking up a partial negative charge, and carbon takes up a partial positive charge. Here also the same thing will happen. Halogen will be partially negative and carbon will be partially positive. So what are these bonds? Both the bonds here are polar covalent bonds. Now when the bonds are polar covalent, the type of interactions which are possible between the molecules are the dipole-dipole interactions. Okay, so there will be dipole-dipole interactions. One molecule of chloroethane with another molecule of chloroethane will have dipole-dipole interactions. Likewise, one molecule of bromomethane with another molecule of bromomethane will also have dipole-dipole interactions. And when you will mix the two, chloromethane and bromomethane, even then between these molecules the type of interactions possible would be dipole-dipole only, and therefore again the interactions are remaining the same even on mixing. So the solution behaves ideally. One more example that can be considered is that of benzene mixed with toluene. When benzene is mixed with toluene, both these compounds are what? Both these compounds are aromatic hydrocarbons. Okay, they are both aromatic hydrocarbons. If you talk about the type of interactions, there is not much difference. Here also the type of interactions possible are the van der Waal forces, because there is no charge separation. When there is no charge separation in the molecule, then the type of interactions possible are the van der Waal forces. So benzene with benzene interacts with van der Waal forces. The toluene molecule with another toluene molecule also interacts with van der Waal. And when you even mix them together, then also the interactions will remain van der Waal. So again the forces are remaining the same before and after mixing. That is the reason why even this behaves as an ideal solution. Now I'm showing you the variation of vapor pressure with the mole fraction in such cases when a solution behaves ideally. So when we are going to plot vapor pressure with the mole fraction, okay, of any one of the components A or B, what type of behavior will be? It will be, it will be obeying the Raoult's law. So this will be the variation of PA, which will be equal to P naught A into chi A, and this will be the highest point P naught A. Likewise, similar will be the variation of PB, which is equal to PB naught into chi B, and this highest point is PB naught. Okay, so this is chi A. As the mole fraction of A increases, the partial pressure of A increases, becomes maximum here. And as the mole fraction of A is going to increase, the mole fraction of B is going to decrease. Let me just show it as 1 to 0 chi B. So chi B at the same time will decrease, and therefore the pressure for PB is going to decrease. And this to this, when you join, this is the curve for total pressure, which is equal to PA plus PB. This graph we have already talked about when we discussed the vapor pressures of liquid solutions. And so in ideal behavior, the Raoult's law is perfectly obeyed. PA is equals to P naught A into chi A, PB is equals to P naught B into chi B, and PT is equals to PA plus PB. So this type of a curve is observed for an ideal solution. Now we talk about non-ideal solutions. So first of all, let's see what is a non-ideal solution or how is it defined. So a solution that does not obey Raoult's law over the entire range of concentration. So what is a non-ideal solution? A solution that does not obey Raoult's law for the entire range of concentration. Such solution is a non-ideal solution. So if it is not obeying the Raoult's law, you know what? If it is not obeying the Raoult's law, PA will not be equal to P naught B into chi B. PA will not be equal to P naught A into chi A. Okay, and PB will not be equal to P naught B into chi B. Right? Remember the expression for the Raoult's law? PA is equals to P naught A into chi A, and PB is equals to P naught B into chi B. But here what? Here it will not be equal. So PA will be either higher or lower than the product of P naught A into chi A, and PB also will be either higher or lower than the product of P naught B into chi B. Now what will be the situation? It depends on what type of deviation from the Raoult's law is observed. So these non-ideal solutions, they are of two types. Okay, let's talk about these two types. The two types are: one, non-ideal solutions that show a positive deviation from the Raoult's law, and second is those solutions, they show a negative deviation from the Raoult's law. So non-ideal solutions are of two types: the ones which show positive deviation from Raoult's law, and second ones are the ones which show negative deviation from the Raoult's law. Now let's compare these two with each other. Now, what happens in a solution that shows a positive deviation? Here, the partial pressure of the two components, that is PA and PB, as we've already discussed, they are not going to be equal to this. So what is it? Here PA will be more than the product of P naught A into chi A, and PB will also be more than the expected product of P naught B into chi B. And if you talk about here, on the other hand, for the solution which shows a negative deviation, you can expect PA will be less than the product of P naught A into chi A, and likewise PB will also be less as compared to the product of P naught B into chi B. So the actual vapor pressures here are more and the actual vapor pressures here are less. We will see the reason behind this. The next thing that is observed is delta H mixing for positive deviation is positive. The magnitude of delta H is positive. Delta H positive means the process is endothermic. Okay, endothermic means what? Heat is absorbed. So during this process, during the formation of a solution showing positive deviation, heat will be absorbed. On the other hand, if you see here, delta H mixing is equals to negative, and negative means that the process is exothermic, and which means heat is released during the process. Now one more comparison and difference that we observe here is delta V mixing is also positive, and delta V, the change in volume, is a positive value. That means what? That volume increases. During the formation of a non-ideal solution which shows a positive deviation, the volume is going to increase, and on the other hand, in case of the negative deviation, the delta V mixing is negative, which means during the formation of this solution, volume decreases. Now, what are the reasons behind all these things? The answer to it is at the molecular level. So now let's see what are the reasons behind it. You know that there will be three different types of interactions in a solution. AA, which is the solvent to solvent, BB, which is the solute to solute, and AB, which is the solvent to the solute. Now, in case of positive deviation, the solvent to solute interactions are weaker. So these interactions are weaker than the initial ones. Now what happens when the final interactions are weaker? What will happen because of that? When the final interactions are weaker, the tendency of the particles of A and B to evaporate increases. As the final bonds are weak, see, when the bonds are weak, they break easily, and so when the bond will break easily, A and B will evaporate, and when more of A and B will evaporate, what will happen? The vapor pressure exerted will be more, and that's why you see here that the expected vapor pressures, okay, the actual vapor pressures observed are more than what was expected, right? And on the other hand, you can probably guess here what will happen. The solvent-solvent interactions, the solute-to-solute interactions, and the solvent-to-solute interactions, when you look at the solvent-to-solute interactions, the final interactions are stronger. Now, what will happen when the final bond is strong? When a bond is strong, the tendency to break the bond will be less. And so what happens? The tendency of A and B, the particles of A and B, to evaporate decreases. Okay, it will decrease, and when it will decrease, what will happen? Therefore, the pressure exerted is going to be less. And on the other hand, here we can write, therefore, the pressure exerted is more. So this is the main reason for positive and negative deviation. So I'm recollecting. In positive deviation, the final interactions are weak. When the final interactions are weak, the bonds are broken easily, and more evaporation results in higher pressures than expected. Now in negative deviation, when the final interactions are stronger, the tendency of the solvent and the solute particles to evaporate decreases, and therefore the pressures exerted in reality are less than what it was expected. Also, you can here relate the enthalpies with the same fact. See, when the final bonds are weak, so stronger bonds are broken and the bonds which are formed are weaker. To break stronger bonds, more energy will be required than the energy which is released when weak bonds are formed. So more energy is required, and therefore the process is endothermic, where heat is absorbed. On the other hand, when you see here that the final bonds which are formed are stronger. So when stronger bonds are formed, more energy will be released. These were the bonds which were broken, they were weak. So less energy was required and more energy was released. So effectively the process is what? Exothermic, where heat is released. Now let me give you few examples of solutions showing positive and negative deviation. Now the few examples which you can mention here. Number one is ethanol and water. When ethanol is mixed with water, or the second example that you can take here is when ethanol is mixed with acetone. See, in both the cases what happens is, see, ethanol has intermolecular hydrogen bonding between its molecule. Likewise, water also has intermolecular hydrogen bonding. Acetone has got dipole-dipole interactions. Now, when you mix ethanol with water, ethanol will try to break the intermolecular hydrogen bonds between the water molecule, and the bond which will be formed between ethanol and water will be weaker than what is already there between the water molecules. Likewise, here also acetone will try to break the hydrogen bonding between ethanol molecules, and acetone will form bonds with ethanol which are going to be weaker. So the final bonds in both the cases are going to be weaker than the initial. So what happens here is that the final bonds which are formed are weaker than the initial bonds. Okay, final bonds are weaker than the initial bonds, and therefore it shows positive deviation. In negative deviation, we can consider two examples. Number one is given by when phenol is mixed with aniline. So this is phenol, and aniline is benzene with the NH2. What happens is the lone pair on nitrogen and the proton of the hydroxyl group H plus, they enter into intermolecular hydrogen bonding. So what will result here is, this is the intermolecular hydrogen bonding, which is a very strong bond. So when these two are mixed together, very strong intermolecular hydrogen bonds will be formed, and that is why it will result in negative deviation. One more example in negative deviation that you can consider is given by when acetone is mixed with chloroform. What is acetone? It's CH3, C double bond O, CH3, and when it is mixed with chloroform, chloroform is CHCl3. So this is chloroform. Here also what happens is that this hydrogen and this oxygen takes up a partial negative charge, electrons shift here, and this hydrogen takes up a partial positive charge. Why? Because of the electron withdrawing nature of the chlorine atoms, and this negative and this positive end, once again they enter into intermolecular hydrogen bonding. And again I mention here that this hydrogen bonding is very strong. So here also in this case, the final bonds which are formed are much stronger than what it was initially, and again this will show negative deviation from the Rawls law. Now one more last thing that we will compare for the positive and the negative deviation solutions is the variation of vapor pressure with the mole fraction. Okay, for positive deviation and for negative deviation. So if we take vapor pressure on the y-axis as usual, okay, vapor pressures on the y-axis and mole fraction varying on the x-axis, right, from 0 to 1. I am first of all showing the expected behavior. The expected behavior is shown with dotted lines. So it is expected that for the two components, the vapor pressures are going to vary like this, and the total pressure will vary like this. Likewise, here also The dotted line shows the expected behavior, and again the dotted line expected. This is also the expected. But what will it actually be? As we have seen that in a positive deviation, PA is less than P naught A into chi A, and PB is also less than P naught B into chi B. I'm sorry, or we can do it this way. Let's write this as, let's take this as negative deviation, then there won't be any problem. So this is for, let's say, negative deviation, and this one we will consider for positive deviation. Okay, so in negative deviation, the expected pressures are the actual pressures which we expect are less than the product of P naught A into chi A or P naught B into chi B. And in positive deviation, these pressures are more than the product of P naught A into chi A and P naught B into chi B. So dotted was the expected behavior, and what is actually the pressures are less. So this is how the pressure is going to vary. There will be a decrease in the pressure for the two components, and even the total pressure will be lower. In positive deviation, the pressures are more, therefore there will be an increase for the first component, increase for the second component, and increase in the total pressure also. Let's say this is the curve for PA, right? So this is chi A. This is the curve for PA. This one is the curve for PB. This one is for PB, and this is the curve for the total pressure, P total. So this is how you see that in positive and negative deviations from Rawls law. Okay, there is deviation from the behavior from Rawls law, and the vapor pressure versus mole fraction curves are not straight lines, but in negative deviation you see a decrease in the vapor pressures, and in positive deviation you see an increase in the vapor pressures. Now what we are talking about are azeotropes. It's a new term. First of all, let's understand what are azeotropes. So azeotropes are binary mixtures. Binary means two. There will be two components mixed together. So these are binary mixtures having same composition. Binary mixtures having same composition in liquid phase and vapor phase. These are binary mixtures having same composition in liquid phase and vapor phase. What else? And these binary mixtures or these azeotropes, they are found to boil at a constant temperature. There are two substances mixed together, but kind of they behave as one, and they boil at one constant temperature. And this is the reason why that these mixtures cannot be separated. These mixtures cannot be separated by distillation, because to separate via distillation there should be difference in boiling points, but here there will be no difference in boiling points because they will behave as one and they will boil at a constant temperature. Also, these azeotropic mixtures are formed at a specific composition only. These are formed at a specific composition only. It's not that you can mix two things in any ratio, any proportion, and they will form azeotropic mixtures. No, at a particular composition only these are formed. There are two types of azeotropic mixtures. They are, number one, the minimum boiling azeotropes. Okay, one is the minimum boiling azeotropes, and two are the maximum boiling azeotropes. Minimum boiling and maximum boiling azeotropes. Let's try to understand the differences between the two. The minimum boiling azeotropes are formed by solutions that show large positive deviation from the Rawls law. Okay, so minimum boiling azeotropes are formed by solutions that show large positive deviation. On the other hand, maximum boiling azeotropes are formed by solutions that show a large negative deviation from the Raoult's law. So point number 1. Now why are these solutions called minimum boiling is because as you know that this mixture of two substances is going to boil at one temperature. This mixture boils at a temperature, it boils at a temperature which is lower than the boiling points, of the two components mixed together. Okay, components mixed together. So this mixture as a whole boils at a temperature lower than the boiling points of the two components, therefore minimum boiling. And you can guess here what will happen. The maximum boiling azeotropic mixture, this boils at a temperature that is higher than the boiling points of the two components mixed together. So that is why the names are minimum boiling and maximum boiling. Boils at a temperature lower than the two components, boils at a temperature which is higher than the two components. Now let's take one example each. Example of a minimum boiling azeotropic mixture where the solution shows a large positive deviation from the Raoult's law. The example taken is 95% ethanol in water by volume, which means when there is 95 ml of ethanol mixed with 5 ml of water, then at this particular composition this solution will behave as a minimum boiling azeotrope. And one example here of maximum boiling azeotrope is of a solution that shows a negative deviation from Raoult's law. And here the example that is taken is of 68% of nitric acid by mass, which means 68 grams of nitric acid when mixed with 32 grams of water, then this mixture will behave as a maximum boiling azeotrope showing a negative deviation from the Raoult's law.